Hey guys, I just wanted to try and make a quick video to accompany our notes that I've made, and hopefully this will be helpful in terms of you guys and your studying. And so the main thing here is I want to try and clarify some of the concepts that we had in the notes. And so much of this is similar to what's already written, but I've added a few things that will either be outside the notes or that we'll eventually cover later that may improve your understanding now. So, of course, what we started with was the Rubik's Cube, and the idea is there's, of course, some history regarding its development in 1974 in Hungary. But the main thing is that we want to study the cube itself. And, of course, what we can basically see is when you buy a brand new one, it comes in this solved position. And the idea is the puzzle is set up so that you can rotate this and therefore scramble it up and end up with something that looks more like this configuration. And of course, the goal as a puzzle is to return the cube to the original solved position by consecutively rotating one of the 6 faces. So what am I implying here? We don't want to consider the situation where we peel off all the stickers off of the faces and therefore just move them around, much in the way you would do if you were, for instance, 8 years old and stumped. We're truly wanting to simply perform consecutive rotations that don't break the cube or disassemble it and end up back in this original position. So that's our goal. And it may not seem like this is a very mathematical goal because there are no numbers or really even skill involved with such a process. But this is in fact quite mathematical. And this motivates, or this is one of the things that motivates the study of group theory, which is really the goal of this course. And so group theory is not about the study of numbers, but rather about patterns and symmetries. And so I think what we can see here very clearly is there are a number of patterns and symmetries that exist within this cube. Right, so going back to this original part, we can kind of see that each face is symmetric in the sense that they're the same size, same shape, same number of blocks, same number of angles, same sizes of angles. And they differ with regards to, let's say, the colors on each face. But what we can see is, loosely speaking, there is this notion of symmetry when one thinks about the ability to kind of go forward and backwards with these rotations. And that's exactly what we're going to try and study and, let's say, provide some kind of formalism to in this course. So, for us, we're still going to stick with this example. So let's see if we can identify some important concepts about this cube. And the idea is these concepts that we're going to lay out are going to be simple, but they'll serve as the boundaries of our study. Now what that means is they'll help us to define what fits into our theory and what does not. So by laying out these rules, kind of step one with a lot of our problems will be to determine whether or not the problem satisfies those rules that we have laid out. Later on we'll say, okay, if it satisfies these properties, then what extra things can I deduce about this particular object? So some things to think about as we're moving forward is, how did you scramble up the cube in the first place? And how do we go about unscrambling it? Well, we've laid out things pretty simple. They're rotations of faces. And this motivates the second thing, which is what actions do we need? And there are many, many, many correct answers. Now, what I'm trying to motivate here is somehow, what are the primary actions that we use in the unscrambling? And so we can start deciding between, do we want to talk about a rotation being simply a 90-degree counterclockwise, or do we want to talk about it being somehow 270 degrees, or do we want to say that all of those are valid, also including their, let's say, clockwise and counterclockwise counterparts? But of course the things that we exclude are things that aren't complete multiple of 90-degree rotations because they do not preserve the original shape of the cube. So what do I mean? An action must somehow, let's say, map this cube, the solved cube, to this cube, the unsolved cube that is still a cube. So for instance, this intermediate thing that is meant to kind of demonstrate how we're rotating would not be, as is, an action because it is not preserving the original structure of the cube. So even though we're going to be talking about actions a lot, what we have to remember is they are defined on top of some object. And so actions can be thought of much like a function. in the sense that a function cannot be even talked about without having an understanding of what its domain is. And when we change the domain of that function, it can very well change how that function looks. Moreover, if we keep the same domain but give a different function, we can get very different results. So there's a very delicate interplay between the set or object on which the actions act. And that's a key thing to keep in mind, because I think that will help us to clear up some of the confusion that we have. And it'll help make things not feel so abstract. So what actions do we need? And of course there's these questions that are pretty simple. How does the Rubik's Cube differ from chess? Well, with chess there are lots of very complicated rules. For instance, there are multiple pieces that each player has. Each piece can only move in certain ways. And of course, if there are pieces in the way of a certain spot, it limits the potential moves that I can actually make. So there's a very complicated set of rules, and everything kind of changes depending on the actual setup of the board. So the Rubik's Cube is a lot more simple than this, because I can always perform whatever rotation I want to. Moreover, in chess, for a lot of the pieces, you cannot always go backwards once you go forwards. Some of them you can, some of them you cannot. And so there's a lot of kind of things that can change here. But the Rubik's Cube is much simpler and, let's say, a little more beautiful in that sense. Rubik's Cube is also different from poker because you can argue all you want, but you ultimately do not have control over the outcome in poker. There are things that you can do to increase the odds of a particular outcome, but you cannot control it, whereas with the Rubik's Cube, everything is completely controlled and known. So there's a lot of differences between classical games, but these differences are important to make sure that our study is viable. So, of course, we've seen these in the notes, hopefully. There are 4 key observations about this cube that we would like to make. There are a predefined list of moves that never change, for instance, rotations of the respective faces. Every move is reversible by simply rotating in the opposite direction. Every move is deterministic, because if you decide to rotate face 1 by 90 degrees, where face 1 means the red face, for instance, then it will happen. Let's say barring something crazy like you being struck by a meteor, but we should not include such philosophical things in our mathematical discussions. And finally, moves can be combined in any sequence. Now, what this means really is, if I wanted to rotate the faces in any combination that I want to, I will always end back up with a cube, in the sense that it will look like something similar to this notation, where we have a 6 sides all lined up, and it's possible the color configuration has changed, but it is still a cube. And so what we mean by the moves can be combined in any sequence is that by doing so, we don't somehow break the underlying original structure. All right, so that's the key thing to remember. It's not saying that, I can just do anything I want to. It's saying that if I have a list of actions that somehow preserve the structure, in the sense that rotations give me a cube once again, then by doing that over and over and over again, I won't somehow magically end up with a sphere. I will always have a cube. And so that's what we have observed. And we could add lots of things to this, such as we could study the colors of each box within each face. We could also mention lots of symmetries in terms of the angles, but those are not things that we need to start out. And so let's say the goal of group theory is to study the mathematical consequences of these 4 observations, or let's say things very similar, or let's say really generalities of these 4 observations. And of course, these observations and our studies using them will in turn help us answer interesting questions regarding objects that have various types of symmetries. And so that's what I mentioned earlier, in terms of we'll first determine whether or not something satisfies observations such as these, and then we'll figure out what more we can determine once we have those observations in our hands. All right? And so this is really what we're trying to build up right here. We have some simple observations, and we're wanting to somehow axiomatize these in such a way that we can do things that at least feel mathematical and will ultimately be very mathematical once we move along in the course. So what we obviously want to do is take our observations and lift them to a level of abstraction that allows us to consider things other than the Rubik's Cube. For instance, in chapter 1, I loosely mentioned that there are things called groups that look like numbers, and of course the Rubik's Cube doesn't seem to look like that. So we would like to remove this kind of language that binds us explicitly to the Rubik's Cube, and that's the goal of the current, or what we're going to do next. And so we want to rephrase these, and of course this abstraction is a big focus of our course, right? This is something that we've seen in the notes, where the goal of abstraction is that it is more widely applicable. And so like I've said before, if we didn't have abstraction, then if you wanted to teach your students, for instance, how to use the quadratic formula, it would be the case that you would have to teach them how to factor or find the roots of all uncountably infinite different polynomials that one can realize in one dimension. And you might say, well, that is ridiculous, because you would do a few and you would get the gist of it. Well, that gist is exactly what abstraction is the notion of the numbers themselves aren't so important, but simply the structure of the equation. The fact that it looks like this means that we can determine various properties about it. And that's what we want to do right here. So, and of course, the idea is there are lots of advantages to this, and you guys can obviously read those lines. Now, so the idea is our more abstract rules still look pretty simple. The idea is there's a predefined list of actions that never change. Every action is reversible. Every action is deterministic. And any sequence of consecutive actions is also an action. So not a lot of changes have happened, other than we have changed the word move in the sense of rotating in the Rubik's Cube to simply action, which can sound pretty abstract in the sense it's just simply some execution of some rule. Now, the thing that I think some of us have been caught up on is that this list of actions given by Rule 2.5 will be thought of as like our building blocks, and we'll call them our generators. Now, let me say this. In Rule 2.5, typically one expects that what is given are your generators. Think when you buy a box of Legos, all the individual Lego pieces. And then Rule 2.8 is simply concerned with all of the things that you can build by combining these Lego pieces in an arbitrary fashion. Now, something to mention is the list given in 2.5 doesn't have to just be our generators. It could be more than those. However, the additional information would be redundant in the sense that it was already, let's say, implicitly given through the generators that we have been given. But typically we'll try and just give us some notion of generators or some smaller set to make our lives easier. Now, I think that these two bullet points are important to really think about, because this is where many of your guys' questions have been stemming from thus far. So, with the above, we'll simply give our unofficial definition of a group, which is really something that's intuitive, not something that we can do lots of rigorous proofs with. And it's that a group is simply a system or collection of actions that satisfy the above rules. And what we'll do later is we'll actually give a much more formal definition with which we can do lots of interesting proofs, but for now we're trying to build intuition. Now, with the Rubik's Cube, let's help to clarify things further. First of all, with the Rubik's Cube, let's say there are generators. And what do I mean by generators? You can construct any configuration of the cube by simply rotating each face 90 degrees clockwise over and over and over again in different orders. And as such, for instance, if you wanted to go 90 degrees counterclockwise, you would simply go 3 90-degree turns clockwise to obtain it. So everything can be written in the language of 90-degree clockwise twists. Now, of course, if I do certain sequences, then I won't be able to tell the difference between them in terms of how the cube looks. So what do I mean? If I rotate one face 4 times, meaning 4 90-degree turns, that's 360 degrees, and you end up exactly at the original position. So if you handed me your cube, would not be able to tell whether you did A, nothing, or B, 4 90-degree turns. Now, this is not a problem, because we'll simply say, in terms of group theory, that action is exactly the same. So we don't double count it, for instance. And this should feel pretty familiar, because in Chapter 1 we talked about equivalence classes, and we should feel okay with the notion of sometimes things feel different in terms of our way of thinking about it, but mathematically we can't see the difference based on the rules that we've laid out. So, and so this is exactly what the next line says in terms of you can rotate it once or 5 times. Now, using Rule 2.8, you can actually prove, and this is a very difficult thing to do, and it was only done recently, that, I'm not even going to try and read this number, but roughly 4.3 times 10 to the 19th different possible ways that you can make the Rubik's Cube look. And you can really imagine that that makes a lot of sense, because if you start thinking back to just permutations in terms of how they're defined in terms of factorials, these numbers get very large very quickly. So there are all these different distinct configurations. However, there are infinitely many possible ways in which I can rotate faces. So what that tells you is there is definitely a lot of repetition in terms of different types of rotations lead to the same exact configuration of the cube. So this is something very important to realize in terms of when you're trying to build your groups in your homework. Just because you've decided that a group has, let's say, 2 explicit actions, you then have to think about what they generate by performing these actions in compositions over and over again. It is possible that you then obtain another action that you have to then count. So this is simply just to give you some notion of how complicated the cube is. Now, a nice thing to understand is every single one of these 4.3 times 10 to the 19th configurations can be thought of as a word where the only letters in your alphabet are A, B, C, D, E, and F. And the idea is this is a very nice way of thinking about it, and we can think of each of our actions. Let's say A is rotate face 1 90 degrees clockwise, B is rotate face 2 90 degrees clockwise, so on, so on, and so on, and so forth. And what you can see is by doing combinations of this, we're spelling inside of the Rubik's Cube group and obtaining different configurations. And this is exactly what I have written here. So what I mean by words are, if I represent my actions, words are nothing other than function compositions in a language that maybe we're more comfortable with. So what does this mean? So, well, for instance, AB would represent starting with the original solved position, rotating face 1 by 90 degrees, and then rotating face 2 by 90 degrees. There's an ordering here that is implied. All right? And you might say, well, when I do function composition, what I do is B first and then A first. And that's fine, right? You can define the way in which that you spell the words to fit the convention that you were comfortable with. Of course, up to some kind of limitations. And these words aren't necessarily unique because A, rotate face 1 once, and A to the 5th, rotate the face 5 times, result in the same exact configuration. So we can see that even though these words look very different, they represent the same action. And so this is just a succinct way of representing function composition. And you don't need to worry so much about this. This is just another nice way to think about it. And so a big question is, does spelling matter for the Rubik's Cube? And what do I mean? So if you have the word ABC, spelling wouldn't matter if that was equivalent to CBA or BAC or any other permutation. And this is a very important thing we want to think about with groups in terms of, does the order of our actions matter? And the answer is yes, it matters. Hence, spelling matters. And this is something that we're going to study. So loosely speaking, a group is just a set of actions that satisfy some mild properties. So you can think the set of actions gives us Rule 2.5, and then these properties of the actions being deterministic, reversible, and closure, which is Rule 2.8, is simply exactly a reformulation of the rules that we had earlier. Now, a generating set for a group is some sub-collection of the actions. So what does that mean? You have all the possible actions that one can do, all 4.3 times 10 to the 19 possible ways of configuring the Rubik's Cube. Then a generating set is some sub-collection of those. And the idea is that sub-collection is enough information to produce all other configurations. So exactly those 6 simple face rotations that we talked about. Now, typically the generating set is much smaller than the whole group, although that's not necessary. And given a generating set, the individual actions in that set are called generators. So back in our previous definition, A, B, C, D, E, F is our generating set for the 4.3 times 10 to the 19 possible actions, and each individual element is a generator. All right. So, and the set of all possible ways to scramble Rubik's Cube is an example of a group. All right. So the idea is when we take all of these actions and put them together into a bucket, which is kind of the idea of a set, then this is a group because it satisfies all four of the properties. And once again, two actions are the same if they have the same net effect whenever they're applied, and that the group, please note the group is the set of actions, not the configurations of the cube. All right, so this is something that I think we're going to struggle with. It's not what the cube looks like. What we are calling a group is simply the actions that you performed to get there. Now, what you should actually see very easily is there is a clear bijection between the configurations of the cube and the actual actions on the Rubik's Cube. So what do I mean? A bijective function is simply something that is injective and surjective, meaning one-to-one and on-to. But really what you should think of as a bijective function means that there are the same number of elements in each set, but they might look different in each place. So a bijection is nothing other than a relabeling. And so in that same way, when we say that the actions exist in bijection with the configuration of the cube, then what you can think of is rather than writing down, let's say, all the complicated positions and things of the cube in terms of the colors of the boxes and so forth, we can simply relabel that in terms of our, let's say, action. That can, of course, be constructed from the alphabet idea that we talked about in the previous slide. So this might seem a bit strange, and we might prefer the Rubik's Cube. However, the action is the easier thing to study because we're removing ourselves from having to really kind of consider something physical in space. All right. Now, something to clarify is, of course, the difference between actions versus generators. So generators, once again, are the building blocks needed for all other actions of the group. Now, the choice of these building blocks are not unique. However, there's often natural choices. So what do I mean? When you took linear algebra as an undergrad, or for instance, when you teach Cal 2, what you learned is, for instance, Euclidean space, which is like the XY plane or the XYZ plane, or not XYZ plane, XYZ space, then you can naturally come up with a basis for the vectors that live in that space. And we typically denote those IJK, where I is somehow this unit vector along the x-axis, j is the unit vector along the y-axis, and k is the unit vector along the z-axis. And what we learned in Calculus 2 or in linear algebra is that any vector in Euclidean space is simply a linear combination of these guys. And the idea is the action of combining is addition. For us, let's say for the Rubik's Cube, what we have is that our bases are these letters A, B, C, D, E, F, meaning rotate each face by 90 degrees clockwise. And instead of addition, we have, let's say, compositions of rotations, meaning the composition is do the first rotation and then do the second rotation. So generators allow us to build up all other actions in the same way that basis vectors allow us to build up any arbitrary vector in that vector space. So, and an action is simply any element in the group. So generators are very special, whereas actions are just anything that live inside the group. So of course, generators are actions, but actions may not be generators. They can be, but that's not guaranteed. All right. So how does this relate to rules? Well, when discussing Rule 2.5, we're typically referring to the generators of the group. Since they build all other actions, this is sufficient. And like I said earlier, it is possible that the list contains more information, but it will be redundant if that is the case. When discussing Rule 2.8, we're referring to the fact that combining generators in an arbitrary way should still be an action, meaning that if I, for instance, rotate my cube a bunch of different ways, I should still have something that is a cube. All right? And so Rule 2.8 is saying that the allowable actions won't somehow break the problem. So if I do these 90-degree rotations over and over again, the cube doesn't magically disintegrate in my hand. It still remains a cube. So everything is allowable because I will once again obtain a cube. So when we're talking about symmetries, what we really mean is the symmetry of the action. in the sense that if I start with a cube and apply the action, I end up with another cube. So there's some notion of symmetry on both sides, meaning like, let's say, domain and codomain of my action, where I started with a cube and I ended up with a cube. And maybe some things shuffled, but structurally there is some symmetry there. And that's what we're saying about not breaking the problem. And so this is once again just describing what I mean in the sense that we have these nice bijections. So let's say the configuration of the cube is exactly in line with our notion of actions. And when I say basically the same, I'm using this phrase very loosely, and we will formalize that later. So for us to break the Rubik's Cube once again would mean that we disassembled it, changed its size, changed its shape, changed its colors, turned it into a different, let's say, any kind of object that you want to think of. Now, I'm not meaning to seem like I'm rambling here. I'm simply trying to clarify the difference between actions and generators to help us better understand the difference between Rule 2.5 and 2.8, which, like I said, is where many of your guys' questions are stemming from. So, for instance, if I ask you to construct a group with a certain number of elements, you do not get to just simply choose 4 actions and call it a day. If you choose 4 actions, you then need to see how many other actions are a result of those actions by appealing to Rule 2.8. So, at this point, I have really went through the notes again, and what I want to do is provide another example that we will talk about in Chapter 3, which is the rectangle puzzle group, and is probably far likely, or it's probably far more easy to actually visualize. So consider a clear glass rectangle and label it as follows. Now what you could really think is get a piece of blank white paper and put numbers at each corner. And what I'm going to do is I'm going to call the configuration right here the solved state of our puzzle. So what you have to understand is there is an ordering of the numbers. It goes from left, it goes 1 in the top left, 2 in the top right, 3 in the bottom right, 4 in the bottom left. That is our solved state. Not only that, we can see that based on kind of my rectangular shape, the longer edge is on top with the shorter edge on the side. So we have a very clear geometric positioning of this shape. So the idea of the game is pretty much like the Rubik's Cube. You want to scramble the puzzle, meaning, let's say, how do I want to say it? Perturb it from this original position, and then the goal will be to return it to this original position. Now, in order for it to be a puzzle, we have to give rules, meaning somehow the allowable list of actions, and for us that will simply be horizontal flips and vertical flips. Now a horizontal and vertical flip refers to the motion of your hand rather than any reference to the axis of reflection. So what do I mean? If you were to grab this piece of paper with both hands, then a horizontal flip would simply be, while holding the paper, interchange the position of your right and left hand when you were holding them on the sides. And a vertical flip would be holding them at the top and the bottom and doing the same. If you feel like my description is not terribly useful, you'll see a picture of this in just a moment. Now, so we're going to talk about this more later, but I think the natural question is, why did I choose those 2 moves and not any of these infinite other things that I could do to a rectangle? So one of the big key reasons, and something I was emphasizing before, is those 2 moves preserve the orientation of the original rectangle. So what do I mean? If we perform those described moves, which are somehow taking this guy and flipping it up versus taking this guy and flipping it over, I still have a rectangle that is short side here, long side there. The numbers change, but geometrically the piece of paper is still oriented the same way. And this is why one of the reasons why I chose those 2 moves. So a natural question is, are there any other moves that preserve its orientation? And there's 2 reasons for asking this. One is you wonder how arbitrary my choice is. And 2, somehow it's possible that from these 2 moves, I'm going to generate other moves that preserve its orientation. And the answer to this question is yes, and we'll see what other moves could be considered in just a minute. Now, if you wanted to explore this problem, what you should do is pause the video, take out a sheet of paper, label its 4 corners, and basically scramble the rectangle yourself using our allowable moves, and then figure out how to unscramble it. All right. Now, of course, I know many of you won't, but I'm simply saying at this point you should try it so that you get a more physical intuition of what's happening here. And this, of course, motivates another big question, which is, do these moves, meaning the actions that I've defined, form a group? Now, of course, if I'm considering it, you imagine the answer is yes, right? You ask your students all the time with bated breath, is this true? And of course the answer is yes, it should be a group. But how do we determine that, and what does the group look like? That's the bigger question. So for convenience, let's say when we flip the rectangle, the numbers automatically become right side up, meaning what? That I can read them, much in the same way when you flip your iPhone around, everything orients correctly so that you can still read it. Now, if you had labeled a piece of paper and tried, it would not be hard to convince yourself that there's only 4 distinct configurations of the rectangle, which is the original, a vertical flip, and this is where you can see I've moved 1 down and 4 up, and 2 down and 3 up. So by vertical flip, I'm not referring to any kind of axis, but simply if I draw this, let's say, middle line through here, I'm rotating about it. There's the horizontal flip, which does kind of the opposite. And then if I do a horizontal plus vertical flip, I get a brand new thing, which is a 180-degree rotation. And I've color-coded things where blue represents starting here and applying a horizontal flip, and red represents starting here and applying a vertical flip. Now, so what we can see is I'm using the configurations to describe it. However, the actions are what are in the group. So the identity action is simply doing nothing. It gets no color. The horizontal flip, which is the blue action, it is in my group. The red line, which is a vertical flip, is in my group. And then a red plus blue or a blue plus red are both equivalent to a 180-degree rotation. So that is also in my group. So you can think there's a brand new action that came from these building blocks. This is something that I was mentioning to many of you guys as you were trying to define your groups. So we have the identity, which is do nothing. We have a horizontal flip. We have a vertical flip. And then we have, if we do horizontal then vertical or vertical then horizontal, we get a brand new action. So let G be this rectangle group. Then the group is a set consisting of 4 actions, but we only had 2 generators. So that's an important distinction to make. 4 total actions, but only 2 generators. So once again, there's the identity, horizontal flip, vertical flip, and rotation, and we represent G in terms of its actions, where we know that we can always relate these back to specific orientations. All right? And what you can see is, of course, there is another possible thing, which is horizontal flip, vertical flip, horizontal flip, vertical flip, and I end up back in the same place. So that sequence of 4 actions is no different than the identity action, so it's not included. All right. And so this is just explaining that the color scheme that I used, and moreover, it's interesting to see that my new action is equal to 2 different looking configurations, but the same result occurs. All right. And it's really this notion of 2 times 3 is equal to 3 times 2 is equal to 6. So somehow the order didn't matter in this particular situation, but it did matter for the Rubik's Cube. And that was because of the extra layer of complexity that we had for the Rubik's Cube. So let's make some observations. Now, since the order of the actions are irrelevant, we actually give this group a special name, which is called an abelian group. And actually the reason for that is this is not a property that all groups have, so it's an extra added piece of structure. So somehow you could say this is another property on top of the 4 that the group must obtain. So I want to say here that abstract algebra is almost a lot like paleontology in the sense of you want to go out and you want to somehow find these objects that live in a particular classification. You want to say, I want to go find dinosaurs. And then it just so happens to be the case that you find a dinosaur, but then it has an extra property, or it has an extra 2 properties. And every extra property that it has somehow distinguishes it more and makes it more special, but it was still a dinosaur. So we have these competing kind of interests of making sure we're in just the most general situation, which was dinosaurs or groups for us, and then it might be something nicer like a Tyrannosaurus Rex and not just any dinosaur, or a billion. Now the Rubik's Cube is not a billion because the order matters, and the way I like to think of this is the difference between putting your socks on and then your shoes versus your shoes on and then your socks. Both of those actions are valid actions. You can do them. However, your desired outcome is typically not to put your socks on the outside. So the order does matter here. Now, another observation that we can make is every, let's say, action is its own inverse. So what do I mean? Well, if I were to do a horizontal flip, I end up here, but performing a horizontal flip again puts the 1 and 4 on the left, which is back over here. And similarly for vertical and for rotations. So every action is its own inverse. So the idea is basically when I reverse my action, it's the equivalent of doing nothing. And so every single one of them reverses themselves. The Rubik's Cube, nor most groups, do not have this property. This is something very special here, but it's an observation we can make. And algebraically, we write it as follows, saying that the inverse of this guy is simply itself. And so this inverse here, you have to remove the notion of somehow a reciprocal. This is not 1 divided by e. There's no notion of division when we're talking about this kind of object. So what we're using here is just this general, let's say, notation for that of an inverse. All right. So in the same way that you can remember from college or linear algebra that when you inverted a matrix, it was not simply dividing by the matrix. It was a complicated process that when I did matrix times matrix, I got something called an identity. So this is simply a notation that represents the line up here. Now, was there anything special about what we've chosen? No, we could have actually generated the same exact set of actions using a horizontal flip and a 180-degree rotation. So what I mean is, if I were to do a horizontal flip and then a 180-degree rotation, it was equivalent to a vertical flip. And similarly, if I were to do a rotation and then a flip, if I were to do a flip and then a rotation versus a rotation and then a flip, or back and forth and so on, everything ends up being equivalent. I know I kind of got a little tongue-tied there, but hopefully you get the gist. Now, what I want to mention here is, and we're not going to worry too much about this because we're going to talk more about these diagrams in the next chapter. This is something I'm just using to hopefully help our understanding at the moment. This diagram and this diagram are actually the same in terms of abstract algebra. And you might say, well, no. I have some crisscrossing here. But if this is just an object, let's pretend like it lives in three-dimensional space. Abstract algebra is really all about the actions, which is really how things connect. And so if you think about this in 3 dimensions, I could take this piece here and lift it up and move it to the other side of this guy, where we're kind of assuming that all of these lines are elastic and will stretch. And then what will I have? Blue line, red line, blue line, which looks pretty much like this guy, except I've kind of, sat on it so it was looking more like a rhombus. But then if they're all stretchy, I can move them back to this square. So the idea was, even though I had 2 different starting generators, I ended up with the same exact set of elements, and somehow the way that everything relates to one another is exactly preserved. And so this is a very important and very fundamental thing that we will be studying as we move forward. So right now I don't want to go into it, but I simply want to use this to, really my goal is to help us better understand the difference between generators and actions and what we actually produce by considering these things. So another nice example that kind of removes itself from, let's say, the world of geometry is simply the integers modulo n. So remember, the integers modulo n are simply the equivalence classes 0, 1, ... n minus 1, combined with the operation of addition modulo n. And this is actually a group. However, this doesn't seem at all like what we've just talked about in Chapter 2. So to kind of avoid, let's say, cheating, we want to really formulate this exactly as we have in Chapter 2. So how do we do that? So we want to somehow convert this into simply a set of actions that satisfy the group definition. So the operation of addition modulo n will be our action. All right, so somehow that's going to be the thing that provides us with our actions. All right, and the idea is if I take a number and I add another number to it from this set using the definition of addition modulo n, I land back in this set. And what you can think of is that's exactly equivalent to the notion of when I rotated a cube, I had a cube again, even though it looked different. Or when I flipped that rectangle, the numbers were in a different place. So in that same way, when I perform addition modulo n on one of these guys, I get another one of these guys. And that is our notion of symmetry.
So let's reformulate this in the language of actions. But first, let's remind ourselves of how this is defined. So addition modulo n is defined as if I add them together and get a number. Then using the division algorithm, I can write this number as a quotient times that number n plus some remainder, where the quotient is just some integer, but r is in the set 0, 1, dot, 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 n minus 1. So when I write like this, a plus b modulo n is simply r. So in layman's terms, this is add a and b, divide it by n, and take the remainder that you get, and that's your answer. Now, moreover, what we have is each of these elements here, 0, 1, dot, 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 n minus 1, these are actually equivalence classes. And what I mean here is these are actually buckets. So somehow I take all of the integers in the world, negative infinity to infinity, but I perform this operation and I end up with these numbers here. Now a nice way to think of this is as follows. Imagine you have a class of 100 kids, and somehow you want to reduce the amount of information you have to consider. So what do? You take your 100 kids and you put them into 5 lines of 20, and then you say each line leader is the representative of that line. And that's the only person that you're really going to interface with. And so in that same way, what we've done here is we said, okay, 0 is not just 0, but it's everybody that stands behind 0 in this vertical line. You can kind of see my mouse implying it. So what I mean is, it's everything that when I divide by n, I get remainder 0. So 0, n, 2n, 3n, 4n, dot, dot, dot. So all of those guys, I'm just going to say, 0's your line leader. That's the information that I want to look at for this particular problem. So every guy that I write here, really, you should be thinking about, we put a bracket around it and we say there's a bucket of numbers. And all of these numbers have something in common with 0. And what is it they have in common? It's when I divide by 5 in this example, I get remainder 0. So even though I didn't put brackets right here, what you should be imagining in your mind is that there are brackets. And these brackets really imply something like this. So this is just a crash course to remind us again of integers modulo n. Now, what's the better way to visualize them as follows? If I have these numbers, I've put them in this list, but there's nothing that stops me from, for instance, drawing them in any way that I want to. So for a nice example, let's fix n to be 12. So we have the set 0 through 11, and let's just arrange them in a circle like this. And what do we have? We have a clock where I have replaced the number 12 with 0. But remember, based on this definition here, 0 and 12 are in the same equivalence class when n is equal to 12. So these are the same numbers, and it is exactly like the clock that you have on your wall in your classroom, for instance. Or maybe they don't do those anymore, but they used to have these on the walls in classrooms. So now I have a very geometric looking object, which makes me feel like I'm closer to the Rubik's Cube. I feel a little bit closer to the idea. Now, the idea is, what I'm going to say is, let's say the hour hand on this clock represents my configuration. So this clock here, representing 12 o'clock, is one possible orientation. But there's also 1 o'clock, 2 o'clock, 5 o'clock, 11 o'clock, and so on. So we have all these different configurations that the hour hand can hit. So we need to somehow construct actions that represent the movement of this hand. And if all is done well, it will still encompass the fact that we were originally talking about these integers with a particular addition operation. So let's think about it. Well, the idea is with this clock visualization, it's pretty easy to understand that if I do some number plus another number mod 12, then what I end up doing is starting at the integer a and rotating clockwise by b units. So let's think about it. What would 1 plus, let's say for instance, 14 mod 12 be? Well, we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spots around. But what we know from the definition is that 1 plus 14 is 15, and 15 divided by 12 has remainder 3. So we are exactly encompassing this in a way, and you should probably spend some time thinking about it yourselves. But once you convince yourself that, for instance, this object and this object are equivalent, then the rest of our study is fairly trivial. So, performing addition is simply rotating the hour hand, and since we're only adding hours or integers in my set, then we will only land on numbers on my clock, meaning I won't somehow end up at 130. So we can trade the set Z12 with addition modulo n for the set of actions, which is choose your favorite element of Z12, meaning pick a number in Z12, and then add any element of Z12 to the one you chose, modulo n. So what I'm saying is all of our possible actions come from picking a starting point, adding a particular number between 0 and 11 to it, and ending up there. If we add some number larger than 11, it is equivalent to one of those smaller numbers. So, and then now in our new visualization, we have a nice way of representing it, which is as follows. The set Z12 is equivalent to the set of clockwise rotations which land on one of the integers 0, 1, 11. So my actions are simply all of the possible ways that I can configure this hour hand on this clock. All right. Now, our question, of course, is this a group? And we know it is, but we need to verify it using the rules that we have laid out. So what we know is it's easier to answer this question if we have a set of generators. So what are the generators for this? Well, for us, I hope it's pretty obvious that basically the way that time works is it ticks along 1 hour at a time. And if you wanted to end up at 6 o'clock, you can either add 5 hours or count forward by 5 1-hour ticks that are equivalent. And so based on the way things are set up, and it kind of hinges on the associativity of integer addition, then our clock can be, so let's say any rotation on our clock can be attained through multiple 30-degree rotations, which is equivalent to adding the number 1 modulo 12 a bunch of times. So we have a single generator right now, which is adding 1. And hopefully what you can convince yourself is, I can move 0 to any spot on here. So if I wanted to move 0 to 10, I can either add 10, or I can add 1, 1, 1, 1, add 1 to get here. So this is our generator. There are others. However, this is the simplest one. So please convince yourself that any configuration on the clock can be obtained in this fashion. And in the same way, any integer in this set can be obtained in that fashion. So what do I mean? If you pick any random integer in this set, and if you add 1 to it enough times, you will obtain any of the other integers in this set. It has this nice cyclic structure, which is really encompassed by the visualization of the clock. So we have the generators. So let's check the rules. Rule 2.5 is basically trivially true because there are a predetermined list of actions. And basically the idea is this list consists of the single generator, which is just rotation by 30 degrees. All right. So we have a single generator. And it basically, let's say, builds all of our other actions. And we'll talk about those in a minute, but you should really remember that I can add any number, and that's still okay. So then is every action reversible? Well, yes. And you might say, of course, because I'll subtract numbers. However, we don't have the ability to subtract because the definition was add numbers in that set. And since none of them are negative, I cannot subtract. However, what we know is a broke clock is correct twice a day, and the reason for that is due to the cyclic nature of let's say, the clock time. So, if I want to consider the action of adding the number y in Z12 to the number x modulo 12, then I get a number z that's equivalent to this. So if I want to reverse this, of course we could subtract y, but we don't have that option. So what are we going to do? Well, I'm going to note something funny. I'm going to say, well, if y is in here, then so is 12 minus y. And you should convince yourself of this. But then, if I add z in this very special choice of w, then we get an expression such as this, and then due to the associativity of addition, the y's cancel out. X plus 12 is, when I divide by 12, gives remainder x. So I have reversed it. So I've explicitly constructed a way of reversing it. And you might say, well, what does any of this mean? Well, the idea is pretty simple. On my clock, if I'm at 0 o'clock and I rotate forward to 5 o'clock, the question is, how do I go back? Since I can't go backwards, I simply finish my trip around the clock. And the idea is if there's 12 spots, and if I walk forward by 5, then the distance to finish my trip is just 12 minus 5. So, this is exactly the geometric motivation here. And since x and y were arbitrary, of course, I have done this in full generality, and every action is reversible. Now, Of course, I hope it's clear that every action is deterministic. If you decide to do it, it will be done. Let's say, of course, the confusing part is I've randomly chosen the starting point, right? I've randomly chosen the number 4, but then once I decide to add, for instance, 5 to it modulo 12, everything is completely determined. So it's not random in the sense of the outcome. It's simply, when I say random, I'm meaning that you can do this arbitrarily. All right. And then, of course, we have to ask ourselves if every sequence of consecutive actions is in fact another action. So what does that mean? If I rotate the hour hand over and over and over again by 1 hour increments, or let's say integer hour increments, then will I still be at an integer position on my clock? And the answer is yes. Geometrically, we know that. And so the idea is if I do a sequence of actions, then if I do them one after another, will I still be in Z12? Well, we can prove this in generality, but let's just do it in a very specific example. So what I mean is, if I add 3, then 5, then 7, will I still get a number in Z12? Well, due to the associativity of addition, I can rewrite it as follows. 3 plus 5 plus 7 is 15. But 15 in modulo 12 is 3. And so x plus 3, well, once again, using mod 12, would land inside mod 12. So everything is a well-defined set-up action. So this is a group. And so we have a nice description of our group in terms of actions that is kind of somehow irrelevant of the underlying numbers. And you might say, well, the numbers mattered. Yes, they did. But let's say the actions we've now described very simply, which are adding numbers inside Z12. So we're not so concerned about the things that they act on. Right? So let's be very clear here. So in this kind of simple object right here, I am acting on X with the operation addition modulo 12 with respect to 3. So somehow this guy acts on 12, on X. And so even though I care about how they behave with one another, then what I can say is all I'm really concerned about is what this guy does, adding 3. And what happens is it doesn't matter what number I start with. If I add 3, it's the same geometric outcome. I rotate by 90 degrees. So what we can see is it somehow doesn't care about the base point and some geometric notion. It's simply just rotating the hour hand. So we have that it's a group, and then the next question is, of course, how many actions are in our group? And the idea is, well, all of my different actions, since they kind of don't care about the base point, is all the different numbers I can add. And clearly I can add 0, 1, 2, 11. So there are 12 possible things that I can add. So, in reality, what you can think of is if I take my generator, which is adding 1, if I compose it with itself, after doing that 12 times, I start to repeat. So what we can see is I can do 1, 2, 3, 11, and then when I do the 12th one, I wrap back to 0, and then when I do it again, I'm back at 1. So my actions just start to repeat themselves after 12 distinct outcomes. All right? And in reality, what you should think is that this is pretty expected, because in my definition of my group, there were 12 numbers. So if somehow there's a bijection between them, I can't have introduced extra information. Now, so the last thing I want to do is quickly clarify some things with the homework. So homework, or say exercise 2.1, is place a penny and nickel beside one another on a table or a desk and consider just the action of swapping the places of the 2 coins. So what you can think of is, let's say penny over here, nickel over here. My action is move nickel, move penny. If I apply it again, basically it moves nickel, move penny, so on and so forth. So, but let's try and dissect things very carefully so that we can understand how to approach each of the other problems. When I say consider the action, what I'm basically doing is providing you with the list of generators. So at that point, Rule 2.5 is satisfied because we do have a predefined list. And so now the goal is really to verify that Rules 2.6 and 2.8 are true. So I hope that clarifies things. There's always a list of actions because I have to tell you something. And so the idea is, will that list of actions be sufficient to satisfy the rest of the rules? So let's walk through the rules. Every action is deterministic because if I make the conscious decision to swap the coins, they will be swapped. We're ignoring the crazy outcomes, such as, like I said, being struck by a meteor and completely destroying the coins. So the only outcome, if I decide to switch them, is that they will be switched. Every action is reversible because if I swap the coins, I can undo it by swapping them again. However, what you want to note is it's rarely this easy to reverse the actions in a group. For instance, with the Rubik's Cube, you can't just perform the same operation again. You're not guaranteed to end up back at the original position. So this is a very special situation. And so the final and somewhat confusing rule is every sequence of actions is again an action. So I hope this is obvious because why? Swapping pennies and nickels will basically either give me the configuration penny on the left, nickel on the right, or nickel on the left, penny on the right. There's no other possible outcome. And even if I swap them 1,723 times, I will still end up in exactly one of those two configurations. So what this means is every possible sequence of actions, and since I only have one action, you just have to ask yourself if I do it over and over and over again, or one given action, let's say, then I have to make sure that I don't break the problem, right? Somehow the penny doesn't turn into a dime or anything else like that. And so then we could ask ourselves how many distinct actions there are in this group. And so you're tempted to say one because there's the action of swapping. But what you have to remember is if you swap, that is an action. But when you swap again, it's like nothing happened. And so the double swap is like an identity action. So what we have is somehow, let's say, the perturbation and then the non-perturbation. Meaning somehow either if I do these actions, either something changes or it doesn't. So there's exactly two configurations that we can have with our penny and nickel. All right. Exercise 2.3 is imagine you have 5 marbles in your left pocket. Consider 2 actions, which is moving the marble from your left pocket to your right pocket and moving a marble from your right pocket to your left pocket. Is this a group? Now, many of you guys have raised some interesting points, so let me try and clarify. Once again, I have provided you with the generators, so rule 2.5 is true. And so many of you really raised questions about the problem description. So what has been your description? Well, I have these 5 marbles. Maybe it's not deterministic because I don't know which marbles are that I'm choosing. And that's a valid point. So first of all, let's just assume that they're all the same. But let's be clear. Since I've defined an action to be move a marble from your left pocket, if every marble had a different color, then the movement of that marble would need to have its own action, or else it would just not be deterministic anyways. Right? So the idea is, let's say, loosely, it is implied that all the marbles are the same by the fact that I haven't given you different actions for each different type of marble. However, that was still a very valid concern for many of you guys to raise. So let's just, like I said, assume that we have 5 blue marbles in my left pocket. So, is this a group? So this is deterministic because since all the marbles are identical, then just grabbing a marble doesn't really affect anything, right? The idea is the fact that all the marbles are the same, even if I'm randomly grabbing it, the outcome is exactly the same. I grabbed a blue marble and I moved it. And we'll once again omit kind of those strange situations like that I start to reach for my pocket and something stops me, right? The idea is we're just going to assume that you can get the marble and move it because that's implied. Obviously, every action is reversible because if I take a marble from my left pocket and move it to my right pocket, then from the given information in the problem, I can grab into my right pocket and move it back to my left. So this is different from the previous situation, right? Every action is not its own inverse, right? If I do move from left to right and then I move from left to right again, I didn't move the marble back. I simply moved more over. So this is a different scenario than what we had before. However, rule 2.8 is not true, and I think this is where we start to struggle. So when I say every sequence of actions, I think what some of us interpret this as is you should go left to right, then right to left, then left to right, then right to left. You don't have to do it that way. So for instance, if you start with 5 marbles in your left pocket and you attempt to move a marble from your right pocket to your left, you cannot even perform that action. Immediately, step 1, it's broken. But even more than that, if I wanted to perform the action move a marble from left to right 6 times, then I would do it for 5 times, and now my left pocket is empty. And when I try and perform that final movement, I have nothing to move. So my problem breaks in that sense, right? The symmetry here is the ability to move a marble. There is a marble available for movement. However, that immediately breaks because once I move all my marbles out of one pocket, I can't move any more out of there. So my actions aren't defined in such a way. So I cannot perform that same action 6 times in a row. So even though I had generators, deterministic, and reversibility, I have it being the case that for this particular given scenario, these actions are not allowed. So what was very important here was not only the actions, but the set, or let's say the object on which they're defined. Right? If I said I had an infinite number of marbles in my pocket, or in each pocket, then clearly this would be a group because I could perform everything as desired. But I've given you a scenario where the object on which you can act is yourself with 5 marbles in your left pocket, and that's it. So then you have to ask yourself, can I do any possible combination of my rule or my actions and still not kind of break the scenario where you have 5 marbles and you can only move them in this way? And the answer is yes, we can break it. So no, it is not a group. All right? And so it's a very important concept. So really the idea is pretty similar to the notion of functions and domains, right? A function can be pretty nice on one domain but pretty bad on another. Think of the function 1 over x, right? It works very well on the set 2 to infinity, but it is very poorly behaved on the set -1 to 1 because it's bad at 0. So what we can see is the domain, which was kind of let's say, analogous to the notion of you having 5 marbles in your pocket, was a poor choice for our set of actions, which you can think of as being your functions. All right, so I just wanted to talk about these 2 exercises because hopefully that helps us understand the rest of them. And so, of course, if here's my dogs, but if you have questions, you should email me. If you find typos or anything like that, you should email me as well. But the main thing is work on this assignment for the rest of this week and go back through these notes. And maybe what I'll try and do is make sure that I give us 2 weeks on things from now on so that we have time to really digest and think about them. But the main thing is really make sure you're understanding this and, of course, asking me and not going to the internet and cheating. But so, sorry for the lengthy video, but I wanted to make sure that we were able to get the deepest understanding of this that we can.